Today, I will talk about one of the main topics I have been working on over the past few years about how we leverage the diffusion as a generative prior to solve the inverse problem. So as Brian just mentioned, so my research is mostly in the cross-disciplinary for the medical AI. So I may also include some applications that I think will be very valuable and important about the medical imaging, which is also one of the important inverse problems that we are caring about and also trying to solve. And I know this similar mostly focus on the Monte Carlo sampling, and absolutely, I'm not an expert compared to the audience here in this domain, but I want to share something from the perspective of the diffusion-based generative model, which also relevant to some like the Monte Carlo sampling, and also how can we do the generation, and also further how we leverage this to solve the inverse problem. So feel free to raise your question. We will also have the Q&A and at the end of this talk. And if you have any question, feel free to raise that. Okay, so let's get started. This is the agenda for today's talk. I will firstly introduce some like a very basic tutorial about the generative diffusion model or the score-based model. So this is suggested by Guanyang to make this kind of the background of the diffusion model to be more comfortable for the audience here. And then I will get into the application, briefly mention the image generation, and also mainly focus on solving the inverse problem using the diffusion. So that's the plan. For the first section, we do have like the two main different perspectives to understand the diffusion model or the score model. And I will mention them briefly from both aspects and mainly focus on the first one, the score-based generative model. And the slides here is adapted from a very good tutorial from Yang Song on his website. So if you are interested, I suggest you to also look into that for more details. So what is the generative modeling? If we look into the goal for generative modeling, we actually aim to sample or synthesize the new data points from the distribution. And if we look into the previous graphical models or the flow models, so there have been a bunch of the methods proposed, the likelihood-based generative models. So they're trying to directly learn the distributions, PDF, or the probability density functions through the maximum likelihood. But there also need to be some carefully model design to make the normalization constant for the likelihood computation can be tractable. So this has been years of the research along this line to design such kind of the generative model to understand the data distribution and also to enable the data generation. And later on, we also have seen the series of the work motivated by the implicit generative models. For example, from the generative adversary network or adversary training. We were trying to use this scheme to learn the distribution through this kind of the adversary scheme, which means like we may not explicitly to represent the probability distribution, but the nerd model can still get the ability to sample or generate the new data that close to the training distribution from some random noise, for example. But this also very well known, like the GAN-based training may be unstable and may have some like very well-known model caps issues in this kind of the tricky training scheme. So this is also something we have seen over the past few years. So how can we, if we can be able to propose a better idea that can be able to understand or capture the data distribution and also enable the data sampling or generation. So that comes to the key motivation from the very beginning for researchers to think about and also establish or about like the generative models on the score function. So if we step back to think further from the very beginning, like how can we present the distribution? If we give in some data set, for example, the samples from unknown distribution Px, and if we have some samples from x1 to xn, and we may want to model the probability density function of the distribution through some like probabilistic model or the energy-based model I'm showing here. The function f here is parameterized by the theta, which means some model parameters that we want to use for the parameterization. And by maximizing the log likelihood of the sampling data, we're trying to train the p theta x to parameterize the distributions that we're interested in using some model parameters data here. But note, like, since we're trying to represent the distribution through the PDF, and we know like the summation or the integral of the PDF should equal to 1. So this will introduce some very important normalization constant that we need to learn in this kind of the PDF modeling. But unfortunately, this normalization constant may be intractable, which will also rely on what kind of the model parameter or the theta that we're using here to parameterize the f or the p. So given this kind of the challenge, and also although the previous work have been introducing like the graphical based model or the game-based model to learn this kind of modeling, if there is any alternative way that we can avoid this kind of intractable normalizing factor, so that comes to one of the concepts called the score function of the distribution. What is the score function? So that is actually described or defined as the gradient of the log probability density function of the px here, as notated. And if we want to learn the distribution through the parameterization or through the learning of the score function, we may have another model that is denoted as the S data here. With the parameterizations of the model parameter data, we want to use this model to learn the score function that can estimate or approximate the real score function from the true data distribution Px. So how can we do that? And also why we care about this? If we think about the gradient of the PDF and through some like the simple derivation here, we can say like the learning of the score function can be able to avoid this kind of the normalizing factors of the z using the formulation we just have based on the energy-based model. So which means that the score-based model could be independent of the normalizing constant. So that will be very natural and also easy to address the intractable challenge that we have been facing, as mentioned in the previous slides. So how can we do this? How can we learn or train the score-based model? And one of the straightforward idea is to minimize this kind of what people call the Fisher divergence, which is actually the L2 constraint or the L2 distance between the ground truth data score function and also the score-based model we are learning here. And through the previous theoretical research, there have been different ways to use the different objective in order to get this kind of training objective by avoid the access to the true distribution of the score function. Because here, we actually don't know exactly what is the ground truth score function here. But through some like the previous method called the score matching, we could be able to avoid access to the true distribution in order to train such kind of the L2 distance between the score-based model and also the true score function. So feel free to look into those papers to look into further. But for here, in order to introduce the high-level idea, we can just understand like, okay, we can do some practical way to train a model that could that could minimize the distance in this L2 norm in order to help us learn the score-based model. So suppose like we may have learned some score-based model, which is denoted as S data here. How can we do the sampling using such kind of estimated score function? And this may come to something that will be relevant to the topic of this seminar. So we actually could use the different MC procedure to sample from the distribution Px using only the score function. For example, the long-term dynamics here. And if we suppose the epsilon or the steps is small enough, and also the sampling steps is sufficient large, and theoretically, we could think like, okay, this sampling could converge to the true distributions Px, as shown in this figure. So this is the very basic concept for the score-based learning and also the sampling through the score matching to training the objective of the score model estimation and also the true distribution score function, and then use long-term dynamics for the sampling to get the new data from the PX through the estimated score. And this has been shown to be the very fundamental way for learning the score function and also for the sampling. But actually in practice, it doesn't work very well to give us or generate the high quality images. What's the reason for that? So in this tutorial, the author mentioned one from a very intuitive way. It's because like the estimations for the score functions, especially in the low density regions, cannot be estimated very accurately. So as shown in this figure, where we have two Gaussian modes, and also we have the samples from the whole distribution. And because in the low density regions, we may not be able to get the sufficiently frequent sampling in those regions. So when we are using the score match objective to estimate the score-based model based on the sampling from the PX, the estimation for those low density regions actually will not give us an accurate estimation of the score function, so which is showing as the red regions in this figure. So in this way, because we cannot get a good estimation for the score function in those regions, so when we are doing the sampling, and the long-term dynamics may accumulate the errors in the sampling process that cannot give us really a good quality image from the real ground truth distribution. So how can we solve this? One of the solutions that is proposed by the author is, okay, we can perturb the data points in the original distribution with the noise, and then train the score-based model to estimate the perturbed distributions on the noisy data points. So the intuition behind this is that if we add the noise, and if the noise magnitude is sufficiently large, so this can populate the low density region in the original distributions to improve the accuracy for the estimated score. So as shown here, when we're populating this kind of the Gaussian by adding the noise, and then we may have a better chance to get more samples from those low density region, and then be able to estimate a more accurate score function from those regions. So this is the intuition behind. And how can we add, or how can we choose a good noise scale for this perturbation process? Because you can consider if we perturb it too much, and then the perturbed distribution will be far different from the original distribution. And if we do not add enough noise, then we may still have this kind of low density region that cannot be estimated in an accurate way. So in order to do this, so in the first papers about this kind of score-based generative model sampling design, the author proposed the idea to add the multi-scale of the noise perturbation. So which means that if we assume we have a set of the noise perturbation with an increasing standard deviation as shown in the series of the sigma here, and we can perturb the original distribution PX with the changing or increasing standard deviation of the Gaussian noise as shown in this kind of new perturbation noise distribution. And this will give us the noise perturbed distribution noted as the P sigma I with the different noise scale of the sigma I. And note like this distribution is not exactly the same as the original distribution PX because of the adding of the Gaussian noise. And how can we sample from this distribution is also straightforward. We can just sample from the original distribution PX that we already, we can sample from the ground truth data, and then adding the noise with the different scales of the standard derivation. So by using this kind of formulation, this comes to the original idea for the design of the noise condition score network, which means that here, we're still using the similar idea to train some score function, the score-based model to estimate the score function, but it's the score function for the noise perturbed distribution. And with the different scales of the noise that is added, And we can see this kind of the distributions of the noise perturbation will also vary different, depends on what kind of noise scale it is. And in order to, after we train this kind or estimate this kind of the perturbed distribution score function, and how can we do the sampling? It's also similar to the previous standard way, but here, since we consider for the different noise scales in the different noise perturbed distribution, so we can use annealed non-driven dynamics to do the dynamic sampling for the different perturbed noise distribution by decreasing the noise scale step by step. So as shown here, we can firstly do the sampling to generate the data from the perturbed distribution with a larger noise scale, and then gradually decrease the scales of the noise, and then finally converge to the original distribution px that we want to really draw the sample from. So this can applied for the real data sampling or the distribution, for example, in the image, by running this kind of annealed non-driven dynamics to remove the noise from the noise perturbed distributions with a larger scale of the noise, and then finally converge to the distribution that will be closer to the clean data distributions or the real distribution px that we are interested in. And this also gives us the very promising results that for the first time we can get or generate the high quality images that is comparable to the GAN model in this kind of the version 2 of the NCSN model. And one of the further interesting aspects following this kind of the noise perturbation, training of the score function, and also the sampling is to extend this to the continuous domain. So we know, like to solve as a solution for the stochastic differential equation or the SDEs, that will always give us some like the stochastic process with continuous selections of the different variables that could capture the distributions at the different time points. And if we expand the previous methods to the noise scale that can be sufficient small until like the infinity, and we can perturb this kind of data distribution with such kind of the continuous growing level of the noise. So in this kind of way, we actually represent this kind of the noise adding process through a continuous time stochastic process. In order to best understand this, just to give some like background information to recall your memory about the ODE and also the SDE. So not like in the SDE, we always have two terms. One is about the drift coefficient, and other is about the diffusion coefficients that will be relevant to the stochastics from the Brownian motion or like the Wiener process. And this can also apply for the case or application here. We can design such kind of the stochastic differential equation where the solution will give us the stochastic process that can describe this kind of noise perturbation process in the perspective of the continuous time perspective. And if we solve this kind of the if we are trying to use this kind of process to represent the perturbation process, that will give us this kind of data perturbation by representing this continuous collections of the random variable from the beginning of the time point of the 0 until the ending of the time point t. And if we solve this kind of SDE to get the solution, and that will give us the reverse process, like how can we reverse the SDE for generating the samples from the time capital T to the time 0, which is actually from the clean data time points. And if we look into this kind of solution of the SDE, we can also notice like, oh, actually, there is one term that is relevant to the score function we just mentioned in the previous approach. So this is also makes it reasonable to say like what's the align or what's the relationship between this kind of continuous perspective versus the previous noise perturbation perspective. And if we are trying to solve this kind of the SDE by designing that in the forward process and also to get the score function estimation in the reverse process, and this will enable us to do the sampling from the pure Gaussian noise to the clean data through this kind of the continuous noise, the denoising process to generate from the noise to the data. So this comes to the basic idea or the fundamental theoretical support, like how can we do the diffusion for the sampling from the prior Gaussian distribution. And in order to train such kind of the score function, which is a continuous time point, which also called as the time-dependent score-based model, we also use a similar idea to minimize the distance between the score model and also the true distribution to score function, and using the similar ideas of the score matching as mentioned before. And here, we also, after we train such kind of score-based model, we can plug in that into the solution of the score of the reverse SDEs, and then to use this as the steps for the sampling in the continuous perspective, and then to do the sampling from the noise. And in order to solve this reverse SDE, we can use the numerical SDE solvers that could be the different kinds of the types of solution by discretized SDE using the finite time steps and also the small Gaussian noise to further do this kind of the implementation in the practice. So this comes to the end for the first introduction or tutorial about the score-based generative model. So in this case, just a quick summary, you may see like how we gauge this kind of the score SDE function design, and how can we train the score-based model based on the time steps, and then to gauge the reverse SDE process for the sampling or the generation process. And for the next step, I will also briefly mention from the perspective of the DDPM to understand the diffusion model. And due to the limited of the time, I will not mention all the details here, but there are also very interesting theoretical derivation and also the fundamental knowledge that could help you better understand how the DDPM is derived from the very beginning of the motivation. So just to briefly mention, in the high level, the original motivation for the DDPM, I would say maybe more from like the denoising perspective. So it's considering like we can use the forward diffusion process by adding the noise and then do the denoising in the reverse process in order to generate the clean data from the distribution. And in this process, in the formulation of DDPM, it used the conditional Gaussian distribution to formulate the forward process across any two adjacent or neighboring time points. And this will come to some important kappa parameters about the noise scheduler that is noted as the beta t here to denote the variance of the Gaussian distribution at each of the steps, which is also equivalent to like the different noise scales as we mentioned before in the score-based model. And in this way, we can gauge a very good formulations in the forward process regarding for each of the time steps versus the clean data in the X0. So again, I will skip some more details here. But more interesting and also important part is in the reverse process. So even though the reverse process, when we consider this kind of the conditional distribution of the pxt minus 1 giving the xt, this is intractable, but we can use a Gaussian distribution to approximate this conditional distribution given the noise scale or the step is small sufficiently. So that is the key assumption in the DDPM to formulate the reverse process. And how can we know this kind of the mean and also the variance for the for this conditional distribution? That comes to the network training, where we are using such kind of the denoising autoencoder to estimate what should be the mean values for the denoising in each of the steps in the reverse process of the diffusion. So this is just showing some like the basic or fundamental implementations for learning such kind of the denoising in each of the steps. And since we are trying to do the denoising at a different t, so you can see here, we also use the time representation t as a conditional information injected into the unit learning, which can give us or predict the noise in the current time steps. And by doing the denoising or extract the predicted noise from the current images in each of the steps, we could be able to do this kind of denoising process or sampling process step by step and finally to generate the clean image. So this is the high-level motivation of the DDPM, and feel free to look into the original paper for more like theoretical or mathematical proof and to understand what's exactly happening to derive such kind of the training objective and also the sampling process. But here I just want to highlight one thing is about relationships between the DDPM and the score-based model we introduced in the first section. So since we have such kind of the different perspective to motivate us do the sampling process through the score function learning or through the step-by-step denoising. So are they exactly the same thing or are they actually the different modeling? So in some following up papers, so they're actually showing some very interesting fundamental alignment and also relationship between these two perspectives. So just to mention something in the very intuitive way, if we consider the formulations of the DDPM, which assume this kind of the conditional distributions in the forward process to be Gaussian based on some like the noise scheduler or the different noise level. And if you write this through the reparameterization tricks by sampling from the Gaussian distribution as the another variable and adding the mean and also the variance, and do some like the discretization to use another assumed continuous function versus the small time steps to represent the beta t, the scheduler of the noise here, and through the Taylor expansion for the estimation and move the xt minus 1 in the other side. So we can actually get this kind of the function that is very relevant and also similar to what we just mentioned in the score-based diffusion models for the SDE function. So this actually meaning some kind of the fundamental alignment between the perspective of the DDPM and also the SDE through the different ways to understand this kind of sampling process and also the different ways to design the modeling in the implementations as well. Okay, so this comes to the end for the basic tutorial about the diffusion model. Yes, things like I took half of the time, so that is great. And I will use the remaining time to more get into the application side by using this kind of diffusion modeling for doing the inverse problem and also the other applications we're looking to. So firstly, the diffusion model absolutely was designed or used for the image generation. This is also the motivation that we mentioned at the very beginning, that we can learn the score function that will enable us to have the generative modeling that can do the new samples to sample the new data or to do the generation of the new images. And following the introduction of the diffusion models, there also has opened the door for many image generation modeling or text-to-image solutions. So just to list a few of them. So for example, in the DALL-E 2, the researcher from the OpenAI introduced this modeling using the diffusion as encoding, while at the same time using the clipped objective or contrastive learning between the text and also the imaging to transfer the embedding between the image and text embedding space, and use the diffusion as the decoder to generate from the embedding to the image, which has shown to be pretty good image generation qualities regarding for some long sentences even. And also similarly, for the researchers in the Google also introduced this imaging model, which introduced the hierarchical level of the diffusion model to help with the text-to-image generation and also to expand or scale to very large scale of the data generation, for example, like the 1024 square images. And it also has shown to be very effective in the text-to-image generations, even with some like the pretty challenging sentence that may not be very common in our real life, but it can still generate high-quality images with the reasonable semantics. And beyond that, I just want to briefly mention, since people have observed some limitations of the diffusion in the training and sampling efficiency, and there are also one kind of the latent diffusion model that has been introduced using the variational autoencoder to project the image data into the latent space, and then to develop or train the diffusion models all in the latent space through this kind of the latent sampling process. And after that, to use the decoder to generate the clean image data out of from the latent to the image space. So the latent diffusions has also shown to be very effective, especially in the computational time efficiency, and also has been shown to generate very good qualities. So that is some like the brief mentioned about the applications in the image generation, and it has been a bunch of the research works following the diffusion introduction and in the recent years in the different generation or image synthesis tasks, which is showing the very powerful ability for the diffusion in generating high quality images. And since my research in the other perspective is focused a lot on the biomedical applications, so what I care a lot about is not only generating some random data. Actually, I care about how can we use a diffusion to solve the real problems that we're facing in the medical imaging, which essentially is an inverse problem, not a pure generation problem. So in this sense, I will introduce maybe firstly to give some brief background about what is the medical imaging and what is actually the inverse problems we are formulating here, and then get into the technical details, how can we use diffusion as a strong prior to solve this. So for the medical imaging, there are different modalities. And just to list the two of them, which has been very commonly used in our clinical practice. The first one is for the X-ray computed tomography imaging, where you can see like showing in this kind of scanner. What it's doing is that we got the projection from the based on the X-ray resources through the patient's body, and then to get the signals projected on the detector. So in this way, we can be able to reconstruct the cross-sectional slides showing the internal structures of the patient's body from the X-ray projections, and also at the different angles when the X-ray resources is rotation in the different degrees or different positions around the body. And this is showing some like the specific examples, how can we get the projections and how can we do the reconstruction. If we have a dense sampling of the projections at a different angle, and it will be able to reconstruct the artifacts-free images of the 3D data, for example. But usually the CT scanning will expose the patients to the radiation dose. So which means that if we could reduce the sampling from to get the projection from the fewer angles, and then that will be much better for patients to reduce the radiation exposure during the CT scanning. But in that way, if we're using the conventional approach for the reconstruction, so you can see the reconstructed images will have a lot of artifacts. And not only for the CT, and in the MRI, which is another modality of the medical imaging, with a similar goal to reconstruct the cross-sectional images of the internal structures of the subjects, but not from the same acquisition space. So here, for the MRI, we actually do the acquisition in the frequency space or the case-based data that you already mentioned in the MRI community. So as shown in the one example here, on the left, we see the sampling in the case-based data. On the right, we see the reconstructed images using the inverse Fourier transform. So usually the MRI scanning will take a relatively long acquisition process. And one of the approach people are doing a lot is to undersample the frequency space data in order to reduce the sampling time or accelerate the scanning. But if we undersample the frequency space data, that will also bring the different artifacts in the image space as shown here in the right figure. So in this case, how can we do the sampling in a smart way, and how can we do the reconstruction to better remove or avoid artifacts in this reconstruction process? That has been a very long-term research in the MRI community for the accelerated or the undersampled MRI reconstruction. So this is just some brief background for the medical imaging. And in order to solve this kind of sparse sampling reconstruction problem, there have been the different motivations in the clinical practice that I wouldn't mention too much here. And just to formulate this as practical or engineering problems, what we call the inverse problem, you can understand in this kind of the formula of the y equals ax plus n. So the A here is a forward process, which is the imaging systems that we just seen from the CT or from the MRI. And the X is the reconstruction target of the high quality image we want to obtain here. And the Y is the undersampled measurements data for like the sparse view of the CT projections or the undersampled MRI acquisition space in the frequency domain. So in order to solve this inverse problem, we want to recover the target X from the measurements of the Y and giving, for example, in the medical imaging, that we know what A it is. To solve this inverse problem, there have been many different approaches introduced over the past decades, including like the statistical methods or compressed sensing. And also in the recent 10 or 20 years, people introduced these data-driven methods, especially from the perspective of the machine learning or the deep learning. So the key idea is that in order to solve this kind of the inverse problem, and we may need to introduce more prior knowledge because of the equiposeness and also because of the sparse information from the given data. So for example, as shown in the right figure, if we are doing the clinical CT scanning in the protocol, we always require like thousands of the projection data to reconstruct one CT image. But if we want to achieve a sparse view CT that can reduce the projection to like below the 100 or 10 projection data, we may need to add some regressizations to further enforce the assumption about the image data to help with the reconstruction process. So that is actually the regularized reconstruction or some specific example like the compressed sensing with the sparsity in the transform domain has been introduced. But given the deep learning introduced, we wonder like, oh, if we could further get a higher level of the prior knowledge from the deep learning model that could help us to learn the prior from a data-driven way that could further push the limit of this kind of the equiposed inverse problem solving. Then the problem comes to like, how can we learn such kind of data-driven prior? There definitely have been the different approach for the deep learning-based reconstruction. I will not get into details there, but I just want to mention actually the diffusion models that we introduced in the first section is one of the very powerful data-driven priors that we can already learn by capturing the data distribution. So again, we have seen like, okay, we can use the diffusion model by training either the score-based model or like the DDPM to get this kind of the forward and also backward process to do the data sampling. And we know like the fundamental assumption here is that we're learning some score function that can estimate the ground truth or the true data distribution that we are interested in. So not only for the medical image, not only for the natural images. So this can also be applied for the medical images. What does that mean is that we can also use this kind of score-based generative model to capturing the distribution of the different CT images, for example, across the different patients. So this can give us a strong data-driven prior, like what kind of the CT image should look like across the different patients, given the distributions that were used to train the model. And in this way, given such a prior, how can we do the sampling to generate the constraint or the conditional samples by combining the information from both the data distribution prior as well as the constraint that we are observed from the measurements Y here. So this is the key motivation for us to think about using diffusion as an inverse problem prior. So if we're considering for the posterior score function, we see like in the unconditional diffusion training, we already have been able to learn some like score function estimation by training on the data that is providing through this kind of the denoising process. And if we're using the Bayesian rule, we can be easy to derive like another term that we need to learn in order to get the conditional generation of the px given y is actually what we already know from the forward process. So this means like the forward operator A, that how can we get the acquisition or the measurements of the y given the image of the x. So since these two terms has already been learned or estimated in some way, so we actually could be able to get the condition generation through this kind of the posterior sampling process by estimating the posterior score function. So if we assume the forward process that we are caring about here is for example, in the medical imaging, that is denoted as the A, which including the physics-based transform in like CT or MRI, and then also along with the sparse sampling of the different view angle or the different sampling pattern. And given this kind of the known operator of the A, and we could be able to design this kind of the conditional or the posterior sampling approach to solve the inverse problem by combining the prior data prior from the already from the trained diffusion model together with the observed measurements. So here we assume like we are doing this diffusion training in a standard way using only the clean data, which is the, for example, the medical images in this case. And in this way, we can get the assumption, we can get the estimation of the score function in the ground truth distribution of the PX. And given the trained diffusion models, we add the information or constraints from the measurements Y as the sequence of the measurements in the different steps, and plug in that to inject the information or constraint of the measurements Y into the diffusion sampling process in order to generate finally the conditional or the posterior samples of the PX given Y. So this is the key idea how we use such kind of the conditional sampling, giving the trained diffusion to as the data prior to generate the posterior samples. And here is some like examples that we are doing such kind of posterior samples for the CT reconstructions from the sparse view samples. And one of the importance or the unique advantage of such kind of methods compared to the previous supervised learning methods that has been introduced a lot in the deep learning reconstruction is that here we actually do not have any assumption about the sampling pattern during the training. So which means that in the training, since we're learning the score function from the distribution, so we are just trying to learn like what the data should look like in regarding for the real ground truth. But only the inverse problem solving process happening is just in the sampling process or in the generation process. And this will make a huge impact in the medical image community because that makes it more flexible and generalizable for a very complicated different medical modalities. For example, the different contrast of MRI or the different organs of the CT, and also the different sampling patterns. Because here we only need to train a single model of the diffusion to capture the prior, which can be applied for all of this kind of the different inverse problems of the different settings. But in the previous approach of the supervised learning, this is not the case. So this really comes with the advantage like for using the diffusion as a prior in solving the different inverse problem. And also following that, there are also different algorithms have been introduced to achieve pretty impressive performance on solving the different kinds of the inverse problem in both like the natural image domain and also the medical imaging domain. So giving all this kind of the remarkable empirical results, even though it has shown to be very promising, but I also want to use the remaining time to briefly mention some about the challenges and also limitations we are facing for now by using such kind of the scheme to train the diffusion as a prior to solve the inverse problem. The key challenge or the limitation actually lies in the computational constraint. So usually we require a very large scale training data to train a good diffusion prior. And also in the sampling process and also the training process, the diffusion model's time efficiency is not very good as the other previous methods like the GAN or the VE for the generation. And also in the other way, the most current methods only apply to the 2D images, and a few of them can really apply to the 3D because of the expensive GPU memory cost for training the diffusion. So even though we have seen the promising of this kind of the scheme, but we are also facing such kind of the challenges or limitations that prevents we really use the diffusion for the real cases. So for example, in the high dimensional or high resolution data for the medical and also scientific domains. Like in the real practice, the CT images or MRI images is always in the 3D dimension. So in such kind of the standard resolution of the 512 cube. But actually for the current diffusion-based methods, it's still very hard to apply this on the real data that we're having in the real world. And not only for the macro images, in other cases, if we consider for the satellite imaging, or if we consider for the dynamic images, and this can also put a lot of challenge in the current diffusion-based methods to make it can really work for such kind of the high dimensional or high resolution data. So how can we enable the diffusion to address this challenge and learn the prior for such kind of the real-time data and further make it can work for the real applications in the scientific domain? So that comes to the research that we're trying to get into in the current days. So for example, if we consider for the most of the previous approach, where we are trying to focus on how can we improve the model performance through the different methods to guarantee the data consistency, and most of them are working for the 2D images. And later on, in order to address this computational challenge or limitation of diffusion models, there have also been a different approach introduced to enable to improve the time efficiency, like the distillation of diffusion or the consistency model. Or there have been the way that trying to improve the data or the memory efficiency, that doing this kind of slice-by-slice reconstruction in order to enable the 3D reconstruction using the 2D diffusion prior. But this kind of methods will also compromise the performance in the cross-sectional slice or the z-axis coherence. And also this will increase the inference time again, because they are doing the slice-by-slice sampling. So how can we really get some improve the methodology that can achieve or get the benefit from both ends to improve the model efficiency while also maintain a good performance of the generation or the inverse problem solving? So in order to solve this question, in the most recent works, we propose like two solutions to address this challenge. One is about the patch-based diffusion, another is about latent diffusion. So I will quickly go through the main ideas of these two solutions in high level in the remaining time. So firstly, if we consider for the 3D image reconstructions, beyond only to consider to reconstruct the 2D slice per slice by slice, and we can consider to know the score function that could be aware of such kind of the cross-slice dependency or the correlation in the score learning. So as shown in the right figure here, in the recent method we propose at diffusion blend, we're trying to know the score function of each slice of the diffusion in each of the time steps, based on not only the score of the data from the last time point, the same slice, but also from the neighboring slice as well. So in this way, which means that we're trying to learn this cross-slice dependency in the training of the diffusion. And this can also enable us to be aware of the slice information through the positional encoding that we're adding to tell the network, like how much slices or how far the neighboring slices is close to each other, to enable us to learn such kind of the dependency across the different slices. Where in this way, we will be able to enable embedding such kind of the information during the training. So not only it totally depends on the sampling time to enforce the cross-slice consistency to get the coherence. And for using this kind of the methods, we could achieve a pretty good like coherence across the different these slices. So as shown in this example, in the previous state of the art, when people are using the total variation as a regression to constrain the cross-slice coherence in the sampling time only, it may not maintain all the detailed informations, especially at the different slices. But if we're using such kind of the cross-slice learning in the score function, that could further help us to improve this kind of the cross-slice consistency over the z-axis. And there are some more quantitative results compared to the previous state of the art in the 3D diffusion. And for now, I think we are achieving the state of art on the 3D medical reconstruction using the diffusion as a prior. And we have another concurrent work, which is not only consider the patch across the different slices, but we also considering the patch across the X and also the Y position to really have such kind of the patch in based the training to enable the diffusion score matching learning with the positional encoding. Feel free to look into the details in our paper, see if you're interested. And beyond the patch-based idea, another idea that we propose as a potential solution is that to leverage the latent diffusion as a prior to solve the inverse problem. So as we mentioned before, the latent diffusion has been introduced to be a very efficient way for the image generation by project from the image data to a lower dimensional space of the latent space. This can also improve like the training and also the sampling time for the diffusion. This looks like to be a pretty good motivation if we want to use this to solve the inverse problem as well, because we can enable this for the high dimensional or high resolution data through this kind of the latent projection. But the challenge comes as how can we enable such kind of the latent diffusion can use as a reliable prior to solve the inverse problem. This is because like with the decoder of the VE, so all the problems will come as nonlinear problems with latent diffusion prior. But in this case, or the previous approach focused on the pixel-based diffusion may not work as well as a reliable way to constrain the data consistency. So in this way, we propose a new method called the resample to guarantee what we call the hard data consistency through an optimization method to guarantee a reliable data consistency by using the latent diffusion as a prior. So the key idea is happening in the following way. So if we consider for the data part, this is how we usually train the latent diffusion. And giving this kind of pre-trained latent diffusion as a prior, in one of the time steps of the sampling process, we can firstly to estimate the clean data given the current unconditional sample to get the initializations of the Z0. And then we do the optimizations giving the constraints from the measurements and also with the decoder that is denoted as the D here and also the border operator A here to optimize the current Z0 to capturing or to inject information to be consistent with the measurements of the Y. And finally, we're doing the resampling process, which projects the current Z0 back to the noisy data manifold in the latent space. And then in order to continue the sampling for the next or consequent step. So in this way, previously, the standard approach is the stochastic encoding, which just to add the noise from the Z0 to the noise manifold at the time t. But here, we find it will be very important to also incorporate the information from the previous unconditional sampling that is showing as the Z prime here. So we propose this kind of the method called the stochastic resampling, which actually combining the information from both the unconditional sampling in the last time step and also the current sample after optimization with the constraints of the Y. And we introduce some hyperparameter to balance the trade-off between these two different information between of the prior consistency and also the data consistency. So if you're interested how we do this, feel free to look into the papers for the theoretical analysis and also the empirical results. So this method has been showing very effective for the different or the general inverse problem. And also one interesting phenomenon we find is that we actually could be able to fine-tune the pre-trained latent diffusion models on the natural images using only a very limited of the city image data of 2,000 samples and adapt that to the city image as a good prior that can be helpful to solve the city reconstruction problem. And we have also shown this not only for the medical image problems, but also can work very reasonable and also even outperforming the previous pixel-based diffusions in the different natural image domain tasks and also the different inverse problems like the super resolution or the inpainting or deblurring. So feel free to look into the paper for like more details about the results and experiments. So finally, as the summary here, so I want to emphasize like diffusion can working as a pretty powerful prior to solve the different inverse problem, but it's facing the challenges to have this kind of the trade-off between the model efficiency and also the model performance. And in the recent works, I just introduced these two key ideas that we proposed to solve to enable the diffusion for the high dimensional and also high resolution data through the patch-based diffusion prior and also the latent diffusion priors. And finally, I want to thank you for all the collaborator and also the funding support, and also my students who has been contributing on all of the works I have introduced today. And if you have any question, feel free to reach out to me through my email, and I'm very happy to take any question.